Good day, everyone. Welcome back to my YouTube channel. This is Sir Marcy. And for today's video, we are still on the second part of our lesson, that is quarter 3, week 6. And the topic that I'm going to discuss for today is all about the right triangle similarity theorem. If you're new to my channel, please consider subscribing and hit the notification bell so you'll be updated with my latest videos. Okay, what is a right triangle? A triangle in which one of the interior angles is 90 degrees is called a right triangle. The longest side of the right triangle, which is also the side opposite of the right angle, is what we call the hypotenuse. And the two arms of the right angle are the height and the base. Below is the example of what a right triangle look like. Take note that this is the right angle and it measures 90 degrees. Okay, opposite of the right angle, which is the longest side of the right triangle, is called the hypotenuse. And the two arms of the right angle are called the height and the base. And these are the parts of a right triangle. What are the different types of right triangles? Broadly, right triangles can be categorized as number 1, isosceles right triangle. In this triangle, one of the interior angle measures 90 degrees, and that is angle B in our figure here. So this one, angle B measures 90 degrees, and the other two angle measures 45 degree each, and that is angle A, which is 45 degrees, and angle C, which is also 45 degrees. That is why this triangle is also known as 45, 90, 45. Take note also, in this triangle, the side AB, take note, side AB here is equal to side BC, because there is a property that states that the side opposite to equal angles are equal.
Another type of right triangle is what we call Escalene right triangle. This triangle is the one in which one interior angle measures 90 degrees, while the other two measures 30 degrees and 60 degrees. In the figure, we know that angle B here is 90 degrees. Okay? And angle A here measures 60 degrees, and angle C measures 30 degrees. Okay? Take note that in this triangle, all the three sides will be of different lengths and the three angles will be of different measures. Let us now discuss similarity in right triangles. First, we start with triangle ABC. We will draw an altitude CD to the hypotenuse. Remember, hypotenuse is the longest side in a right triangle. And to find the hypotenuse, that is opposite of our right angle. In this figure, our right angle is angle C, and the opposite of angle C is side AB, which is the hypotenuse. And then we're going to draw an altitude. That is why we have here segment CD. So notice, drawing this altitude divides the original triangle into two smaller right triangles. The first triangle is triangle BCA, and the second triangle, which is in color blue, that is triangle BBC. Therefore, there are three triangles in the figure below. So if we're going to get a wider view, we have the first triangle, which is triangle ACB, and then we draw the altitude. We have now the small triangle and the medium triangle. So, if we're going to rearrange them, you can see that these triangles are similar to each other. Remember the word similar. When we say similar, they are the same shape but of different measures. So we have here the bigger triangle, which is triangle ACB, is similar to triangle ABC, which is the medium right triangle, is similar to triangle CDB, which is the small right triangle. Let us now move on with the parts of a right triangle incorporated with the altitude. So if this is our altitude, segment CA is the leg adjacent, or this is the leg adjacent to segment AD. Also, segment CB is the leg adjacent to segment DB. Take note that these two segments, we have segment AB and segment DB, are the segment of our hypotenuse AB. Now, we have here the right triangle similarity theorem. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. That is why, if you're going to recall these three triangles, so this simply states or illustrates the right triangle similarity theorem. And there are ways on how you can solve for the altitude or its segment. Let's say segment AC and segment CB, as well as segment AB and DB. So for now, we're going to discuss the geometric mean altitude theorem. The length of the altitude to the hypotenuse is the geometric mean of the length of the segment of the hypotenuse. And to solve for the altitude or the length of the altitude, we'll use this proportion. First, we have segment AB, which is the segment of the hypotenuse all over the altitude is equal to the altitude all over the segment of our hypotenuse. Applying cross product, we will have CD squared is equal to the product of AB times BD. And to solve for CD, that is simply extracting square root. So we have the square root of AB times BD. So let's try to have some examples for us to understand this geometric mean altitude theorem 1.
In order for us to understand geometric mean altitude theorem number 1, so let's try to solve this figure. So in geometric mean altitude theorem 1, we're going to solve for the length of the altitude. So we're going to solve for this side. That is segment SB. So to solve for segment SB, first is we're going to get the side RV. So RV all over, we have this altitude SV is equal to SV all over the side of DT. Okay? So that's how you solve for this altitude. So you just apply cross product, that is SV squared is equal to the product of RV multiplied to VT. Then we apply extracting square root. We have SV is equal to the square root of RV multiplied to VT. Then we substitute. We have SV is equal to the square root of RV, which is 20, multiply to VT, which is 5. Then we have square root of 5 times 20. The answer is 100. And what is the square root of 100? The answer is 10. Okay, so the length of the altitude SV is positive 10. Let's try another example. Suppose we're going to find the measure of h, and take note, h here is your altitude. So again, to find the measure of this altitude, we're going to write the proportion. First, we have m. Okay, so m all over the altitude h is equal to h all over n. And then if we're going to apply cross product, we have h squared is equal to mn. And then applying extracting square root, so this is cancelled out. We have h is equal to square root of nn. And then we're going to substitute. The value of m is 12 multiplied to 8. And what is the product of 12 times 8? That is equal to square root of 96. And then from here, we simplify radical. So square root of 96, that is the same as 16 multiplied to 6. And then we know that 16 is a perfect square, so we can get the square root both sides. Now we know that 16 is a perfect square and the square root of 16 is 4. Since square root of 6 is not or is already in simplest form, so we will just copy square root of 6. Therefore, the measure of h is equal to 4 square root of 6. And we're going to discuss also geometric mean altitude theorem 2. It states here that the altitude to the hypotenuse to a right triangle intersects it to that the length of each leg. Use the geometric mean of the length of each adjacent segment of the hypotenuse and the length of the entire hypotenuse. Take note of this word, entire hypotenuse. So if we're going to solve for segment CA, which is adjacent to segment AD, we're going to use this proportion. AB all over CA is equal to CA all over AD. Then, if we're going to apply cross product, we will have CA is equal to square root of AD times AB. And let's say the missing side is segment CB, which is adjacent to segment DB. So we're going to use this proportion, that is AB all over CB is equal to CB all over BD. Then, to solve for CB, applying cross product here and simplifying this, we will have CB is equal to square root of BD times BA. So let's try to solve geometric mean altitude theorem 2. I have here the summary of the geometric mean altitude theorem. Suppose we're going to solve for C. Okay, to solve for C, we just simply add the segment of the hypotenuse. We have m plus n. If we're going to solve for the altitude, which is h, we just simply remember this. That is equal to the square root of m multiplied to n. If we're going to find the length of A, we're going to use the formula m square root of m times c. And if we're going to find the length of B, that is simply n multiplied to the hypotenuse C. Okay, again for letter B, that is square root of n times C. Okay, so that ends our lesson for today. I hope you learned something new, and if you're new to my channel, please consider subscribing and hit the notification bell so you'll be updated with my latest videos. Goodbye!